So here we go. Section 1.2, we are going to introduce the topic or remind you of the topic because you've likely seen it before of the idea of what a function is, because college algebra, this class that you're in, is the algebra of functions. When we get to, after this first test we have next week, when we get to unit 2, we are going to be dealing exclusively for the rest, almost all the rest of the semester, with functions and why they're important and how they behave and what they look like. So that's why we're taking the time to remind you of this topic. So before we get to that, the first thing that we are going to go into here is we are going to talk about interval notation. Again, something that is likely a reminder for you. So I'm going to move fairly straightforward here through this section until we get to some stuff that you haven't seen in intermediate algebra. So what we're going to talk about is what's called interval notation. And interval notation is the way to write a set of numbers that you can't possibly list all of them. When you want to include every single number, for instance, between 1 and 2, including all the decimals, all the irrational numbers, here's what you're going to do. In interval notation, you choose a lower boundary, and then a comma, and then you choose an upper boundary. Some books say lower limit and upper limit. I'm using the word boundary because when you get to pre-calculus, the word limit means something completely different. And then on each side of this interval, you are either going to put a bracket or a parenthesis, depending on what you have. So I'm just on this little generalization here. I'm just going to use one of each. When you put a bracket on an end of your interval, that means that you have equality, you have an equals sign. And then when you use a parenthesis, it means that there is no equality sign. And we're going to go through here and we're going to do an example of pretty much everything that you'll see as we go throughout the semester. Interval notation will be something that we use pretty much every day starting in Unit B. So it's good to get good at this. So for instance, my first example right here, example 1, says I want to write the following set of numbers in interval notation. I've got the set of numbers x such that, in case you're not used to reading set builder notation, this just says I have a value. That's why I have an x here. This bar is read such that it says whatever comes next are your conditions. And so I've got my values such that my x's are greater than -4 and at the same time less than or equal to 9. Now, I find it's helpful the first time we go through interval notation, in case you haven't seen it, to draw pictures of these. That will help us translate these into intervals. So first, let's draw a picture. So here is my number line. Okay, on the number line, what values matter to me on this number line? Yeah, those are the two values addressed, so -4 and 9. So I just put them on here. Now, at some point in the past, you've had an arithmetic class or an algebra class where you've had to put things on a number line. When I don't have equality on a number line, so I have just a strictly greater than here. When I don't have equality on the number line, what do I put on, when I don't have equality on my interval, what do I put on the number line? You put an open circle. The open circle says that this is the boundary, but the -4 is not included. And then at the 9, what am I going to put since there is equality? You're going to put a closed circle, okay? So graphing on a number line isn't technically part of this class. I just want you to have a picture so that when we write this in interval notation, it's going to be a little easier. And so since my values are greater than -4 and less than 9 at the same time, where am I going to shade on the number line? Left, middle, or right? I'm going to do the middle. Then my values are between these two. Okay, now I am ready. And maybe you could have done this without the picture. That's even better. Now I am ready to write this interval in interval notation. So help me out. What is the lower boundary of this interval according to the picture? What's the lowest value? -4. Yep, so I'm going to put a -4 right here, comma. What's the largest value according to this picture? 9. Great. Now, according to my generalization example, what am I going to put at the -4 end of this interval? I'm going to put a parenthesis. Why am I putting a parenthesis? Because It's open. There's no equality there. So I'm going to put a parenthesis there. What am I going to put at the 9 end of this? A bracket. Why a bracket this time? Equality. Yes, it's just that simple. Once you get the hang of it, there it is. So do exercise 1 right next door, please. Write that set of numbers as an interval. So on this particular problem, what are the values on the number line that matter to me? Yeah, I know that's kind of an obvious question, but I just want to make sure that we're all straight here. Okay, so now at the -11 end on my number line, what am I going to put? Open circle, closed circle. Closed because there's an equals. At the 0 end, what am I going to put? Open circle, great. And where am I going to shade? Left, middle, or right? Again, middle. Okay, there's my picture. And so now here we go. This is what I care about, the interval notation. If you don't need the picture, then don't draw the picture. That's totally fine. And so what's the lower boundary of this interval? What's the upper boundary? What am I going to put at the -11 end of my interval? Why? Equality. What am I going to put at the 0 end of the interval? Parenthesis, no equality. Fantastic. Okay. Please notice this about interval notation. This is super important. This is really the only thing that sometimes students goof up. Number order is important. Intervals always go from left to right, just like the number line. So if you wrote this interval 0 on the left and -11 on the right, you're communicating wrongly. Okay, and there'll be a deduction, not a complete wrong problem, but there'll be a deduction for not using interval notation properly. All right, example 2. So what happens in example 2, the reason I've separated this is now I have an interval that says all of my values are bigger than 6. I don't have 2 endpoints like the previous one. So again, let's go to the number line if we need it. On this particular number line, what's the only value that matters? 6. What am I going to put at 6? Open circle, because there's no equality. And now which way am I shading? Which way on the number line represents those values that are bigger than 6? Left or right? Right. Okay, so here we go. All right. And so that means that goes to the right forever. So here is how we write this in interval notation. What's the lower boundary of this interval? 6. That's the lowest value. Okay. You don't know this, that's okay. We're here to learn. What's the upper boundary? Yeah, there's no upper boundary. So we use this symbol called infinity. It's like an 8 that's been out too late on a Friday night, so it's passed out. Okay, so what that means, remember, infinity is a direction, not a destination. You never get to infinity. Okay, that's just telling you you're going in that way forever. So on this number line, what am I going to put at the 6 end? A parenthesis because there's no equality. Now, what you put at the infinity end has nothing to do with the inequality sign. You always, every time, because you can never get there, you always put a parenthesis with infinity. Okay, so I'm just going to make a little note here. You always use a parenthesis with infinity. Okay, I think you're going to find the next exercise easy enough, but go ahead and do exercise 2, please. So my number line is right here. The only value that matters, again, is 3 on this one. The only difference on this problem, as opposed to my example, is what am I going to put at 3 on my picture this time? A closed circle, because there's equals there, and so now it's greater than, so I'm going to shade to the right. And now my interval. What's the lower boundary of this interval? 3. What's the upper boundary of this interval? Infinity. What am I going to put at the 3 end to this one? A bracket because of the equality. What am I going to put at the infinity end of this one? A parenthesis because it's infinity. It has nothing to do with the sign. Fantastic. All right, I've got one more example, and then this is going to pretty much end our discussion of interval notation. I'm hoping that this is coming back to you, or if you've not seen it in a long time, that it's not too hard to catch on to. So this last one, example 3, I've got the other inequality sign. My values are now less than or equal to -9. So once again, the only value that matters is -9 on my number line. I am almost positive all of you would tell me that I'm going to use a filled in circle because of the equality. But this time, which way am I shading if my values are less than -9? Left. Okay, so here we go. Whee, just like that. And so now my interval. Okay, what would you propose is the lower boundary to this interval? Yeah, so it's going backwards forever, and so it's related to infinity, but to let everybody know that we're going negative infinity. That's great. And then the upper boundary is -9. What am I going to put at the negative infinity end of this boundary? No. Infinity or negative infinity, you always put a parenthesis. That's okay. That's an opportunity to learn, which I'm sure you just did. You will never forget that now again. And now the -9 end, what are we going to put at the -9 end? Say it proud. Bracket, yes, perfect. All right, do exercise 3. Okay, so exercise 3, my values are less than 7, so I'm going to use an open circle. I'm going to shade to the left, just like we did on the previous problem. And so here goes. What is my lower boundary? What'd you write down? What's the upper boundary? Okay. Parenthesis at the infinity end always. And this time, since there's no equality, what am I going to put at the 7 end? Excellent. Last thing about interval notation I'm going to let you know is at the end of our last class, or no, that was my other class. Sorry, I'm getting them conflated right now. So I need to just tell you, how do you write all real numbers as an interval? All real numbers just basically means the entire number line. Everything left, everything right. So because of that, when you write all real numbers, what would you guess is the lower boundary of all real numbers? Negative infinity. 0 wouldn't be the lower bound because then I'd be missing all the negative values. What do you think is the upper bound of all real numbers? Positive infinity. And so there is the mathematical way to write all real numbers as the answer to something. It's negative infinity all the way to positive infinity. Okay. So far, so good. Any questions about interval notation before we get on to the meat of this section that I'm excited to talk about? All right, so what we want to talk about, we need interval notation at certain points to talk about it, is we need to understand what a function is. So before we do that, I'm going to define what is called a relation. A relation is maybe the simplest mathematical object that we'll talk about all semester. A relation is a set of ordered pairs. Relation is short for relationship. You're saying these ordered pairs indicate that these x values and y values are related in a certain ways. Okay, so I'm going to say that this is parenthetical. Ordered pairs define a relationship. So what we're going to do for the rest of the class is we're going to look at different relations, different ways of indicating a set of ordered pairs. And we're going to talk about what they're communicating to us. So notice example 4, example 5, example 4 and example 5. I've given you 3 relations. I've labeled them A and B and C because I am super clever. Okay, so all of those are examples of relations. We're going to come back to page 1, but now we're going to flip to page 2 because before we can have any fun with these relations, I need to tell you now what a function is. A function is a specific kind of relation. A function is a relation, meaning a function is a set of ordered pairs in which each x corresponds to exactly one y value. I'm going to give you a second to write that down. That's super important. A function is a relation in which each x value corresponds to exactly one y value. To think about this visually, or a visual explanation, a function is a relation in which each x occurs once, meaning it's related to exactly one y value. So let's go back to the front page. We're going to look at the three relations there. And I would like you to take a moment for those three relations, those three sets of ordered pairs. I'd like you to write down underneath each of them if it's a function or not a function. Function or not a function. That is what you are, that is what you're answering for me. Does each x occur once? Does each x value relate to exactly one y value? We'll flip here again. I'm just going to go to these examples. Okay, so let's look at each of these. So relation A, would you say that relation A is a function or not a function? It's a function. You can look at it. Each x value occurs one time, and what that means is the x value -2 has exactly one y, 3. The x value 0 has exactly one y, -6. The x value 3 has exactly one y, 5, etc. So this is a function because each x value is listed one time. How about relation B? Is it a function or not a function? Why is it not a function? Which one is repeated? Yeah, 1. Notice 1 relates to two y values. So it is not a function. Everybody see the difference? How about C? Is C a function or not a function? It's a function. The reason I give C is because I just want to make sure that you understand that to be a function doesn't matter what the y value is. It can be all the same y value, okay? But 2 only has one y value. It's 4. 3 only has one y value. It's 4. Okay, 7 only has one y value. It's 4. Now, we will later in the class, I think it's unit C or unit D, we will talk about a specific function where each y value is also unique because there's special properties. It's called a one-to-one function. You don't need to know that right now, okay? But that is just a further detail we'll get to. Okay, we'll come back to page 1 again, but what I would like you to do is for example 5 and example 6, right there, those relations are listed as tables rather than as sets with squigglies. So for example 5 and 6, and also, I guess I've used the words example and exercise just to confuse myself. For the next 4 exercises on the page, the tables and the mappings, determine if you think they are a function or not a function. So the next two problems give us our relation, our set of ordered pairs listed in a table. So example 5, is that a function or not a function? It's a function because you can just go down the x's. Each x occurs once, meaning it relates to exactly one y value. So that's a function. Is everyone understanding the idea of a function? Are we doing okay? This is super important. Okay, exercise 6, function or not a function? Not a function. Why? Yeah, in fact, we have two pairs. -3 has two y values, and also 7 has two y values, so it fails multiple times, so it's not a function. The next two examples give us our set of ordered pairs, our relation as a mapping with an arrow directing you to what x value relates to what y value. So example 6, is that a function or not a function? It's a function. Each x value has one arrow leaving it. You could write this as ordered pairs 2, -4, 7, 5, and 13, 0. So that is indeed a function. Great job. And how about exercise 7? Would you say that is a function or not a function? Why is that one not a function? The -2. How many arrows, if you didn't see it first, look at it now. How many arrows does -2 have leaving it? 2. That means -2 relates to 0 and -2 relates to 1. That's why it's not a function. All right, before we leave page 2, let's go back up to our definitions. There's another pair of words that we're just going to get under our math belts today, and that is domain and range. Again, fairly simple concepts. I'm certain if you took intermediate algebra, you've heard these words before. Does anyone remember what the domain of a relation is? Yeah, it's the set of x values. And how about the range? What is the range of a relation? The set of y values. Yep. Give you a moment to write that down. And then what we're going to do is, for just a few of the selected problems, we're not going to do it for all of them, but we're going to go back. I'm going to do the first one, then I'm going to give you another one to do. So I'm going to flip back for relation A, which happens to be a function. What we're going to do is we're going to define the domain and the range. So I'm going to do this first one right along with you. So the domain of this, I'm just going to abbreviate DOM. The domain, we use, in this case, braces. In the case where I can list things, I use braces. We'll see later that there's going to be times, the majority of times for us in this class, we're going to use interval notation. But what are the x values in this set? Yeah, just the x values. Yeah, -2, 0, 3, 7. Just to address a question or two that students typically have. Mr. Perkins, do I have to write them in number order? It's not technically required. I won't mark it wrong on the test, but it's mathematically proper to put your sets in number order. And, you know, I advise it just because when you have to do things with sets, it makes them easier to look at. And then also, hey, Perkster, if a number is repeated, do I have to write it twice? No, you just write it one time if it's repeated. So in this case, the range, my y values, well, the y values are 3 and -6 and 5 and -2. So I'm just going to write them in number order, -6, -2, 3, and 5. There's my domain. There's my range. If you've got a question, please, you're not an interruption to me. I'm rolling. I'm feeling really good today, so I'm going to keep going. So raise your hand if you need anything. For relation C, which also happens to be a function, please write down what the domain and the range are. What's the domain of relation C? Yep, 2, 3, 7. Thank you for saying it loud and proud. I love it. What's the range of relation C? Yeah, just the number 4. Great. So I'm just going to put that in my squigglies. I'm going to flip the page. I would like you to do the same thing, just identify the domain and range of example 5 and exercise 7, the first and the last of what we just did a few moments ago. All right, so for example 5, the domain, what is the domain of that one? -6, 3, 5, 8, and 11. Fantastic. And then what is the range of that one? -4, 0, 2, and 9. Is everyone tracking? Are we doing okay? All right, then exercise 7, we roll down to the bottom to this mapping. The mappings are fun because you just got your circles there. The domain of that is -2, 1, and 6. And then the range is 0, 1. Everybody still with me? We doing okay? All right, we're flipping to page 3. We're going to continue this exercise, but now we're going to see our relations given to us pictorially. So example 7 on the left, here's what I would like you to do. We're going to put some points in, and we're just going to say, okay, can we identify something as a function or not a function? And can we identify the domain and range if we have a graph now? So there's nothing particularly special about these points. I'm only listing a few just because I don't want to bore everybody. So first one, -4, 2. I'm going to write it down so that you know what it is. So -4, 2, and then 0, -6. And then 5 and 4. And I'll give you a moment to put these on, and then we're going to answer our 2 questions. We're going to do this one together, and then I'll have one for you to do on your own. So those are my 3 points. So firstly, does that picture represent a function or not a function? Yeah, each x is listed once, right? Each x value corresponds to a single y value. So this is indeed a function. Great job. And so then the domain and the range, what are my x values of this function right here? Great, -4, 0, and 5. And then what are my range? What's my y values? Excellent, wonderful. I don't think it's any harder than what we were doing. You're just seeing the relation given now as a picture instead of as a list. So I'm going to give you a relation. So write down these points. The first one is -3 and 5. The second one is -3 and -4. The third one is 1 and 0. The fourth one is 6 and 3. And then the last one is 7 and -2. So there's 5 points. Once you have put all 5 points on your Cartesian plane, go ahead and answer those same 2 questions. Is this a function or not a function? And then what is the domain and the range of that? All right, so this problem, exercise 8, with those 5 points, is it a function or is it not a function? Why is it not a function? Yeah, the -3 relates to 2 y values. Everybody see that? You're tracking with me? we're getting more and more important as every example goes. Okay, now the domain and the range. Okay, so my domain and my range. The domain of this are my x values, which are going to be -3 and 1 and 6 and 7. If anyone got anything different, please raise your hand. Let me know. I love questions. My range are my y values. So that's going to be -4 and -2 and 0 and 3 and 5. Those are my y values. So now we're going to turn our attention from graphs that look like these two problems right here to graphs that look like the next 4 examples. What's the difference? Can anyone describe for me in your own words, doesn't matter, what the difference between the top 2 graphs and the next 4 graphs is? Okay, yeah, it's a hard question, so don't worry about it. Top 2 graphs, I've given you a set of points that you could count, right? 1, 2, 3 points, 1, 2, 3, 4, 5 points. There's when I count, there's a start and there's a stop. But look at example 8 and 9 and these other ones. These are graphs. And when you see a graph, the reason we use graphs is it represents every value, not just the whole numbers, not just the decimals that end, but it also represents all the irrational numbers. So these represent an infinite number of points. I can't count all the points here. I'd never stop. Okay, so we have to approach these a little different. Now, as far as function or not a function, I don't think this is going to be too big of a deal. I want to show you something that occurred on exercise 8, just so that we can take advantage of this. There is a nice, useful tool to help us really quickly identify if a graph is a function or not. Again, you've probably seen this. You probably know what's going on. But notice at -3. At -3, this is where this exercise failed. So notice if I draw a vertical line, I'm going to draw a dotted purple vertical line. How many times does this vertical line hit right there, that graph? Hits twice, meaning there's 2 y values. So this is what's called the vertical line test. And the vertical line test is a quick and simple way to inspect a graph to see if it's a function or not. And the way you determine is if a vertical line touches a graph at more than 1 point, the graph is not a function. Sorry for the small writing there. I should probably put a blank. So I'll improve this for next semester, but you won't be here. You'll be off in pre-calculus, so it doesn't help you now. I'm going to repeat that just in case you can't read my terrible handwriting. The vertical line test says this. In fact, the vertical line test takes a lot less time than writing this down. That if a vertical line touches a graph at more than 1 point, the graph is not a function. So here's what I would like you to do for the next 4 problems. I want you to use the vertical line test real quick, and I want you to determine are each of the next 4 graphs a function or not a function. Okay, I'm going to leave this up here for another moment so that you can write down. So go down to example 8 and exercise 9 and example 9 and exercise 10 and determine are they a function or not. All right, example 8. Is example 8 a function or not a function? It's not. It fails a lot of places. This circle is not a function. I'm just going to draw a vertical line right here as my example. How many times does that vertical line hit the graph? 2. So that means for that x value that the vertical line goes through, that x value, because remember, vertical lines, if you remember this from intermediate algebra, vertical lines all have the same x value. That's why we use it. It represents that x. This x value represented by the vertical line corresponds to two y values. So that is not a function. How about the one right next door, the ellipse, exercise 9, function or not a function? Again, yes, I'm gonna draw an example here. There's my vertical line. It hits the graph in more than one place. So that is not a function. The next one, example 9, the parabola. Now, I just want to let you know a little something. The graphing software I use online, the one thing I do not like about it, draws a beautiful graph. It won't draw arrows for me on the end. So when you have a graph that goes to the end of the thing here, you can assume that there are arrows. So if that happens on the test and you are concerned, come up and I'll remind you of that. Okay, but that's the one thing. If a graph is fully on the Cartesian plane, the software I use will do it like the first two, and there'll be white space around the graph. Okay, so that comes into effect for our next part. But for function or not a function, example 9, is this a function or not a function? It's a function. Notice I can take vertical lines, and every vertical line I draw hits the graph in how many spots? 1, yes. So this one's a function. And then last but not least, exercise 10, it's a parabola that's on its side. Is this a function or not a function? Yeah, again, just like the circle and the ellipse above it, it's not a function. Anyone struggling to identify if a graph is a function or not a function? Are we doing okay? All right, before we leave this page, one more thing. I want to identify the domain and the range of these. And this is where our new friend, interval notation, comes in and why we spent a moment talking about it. Okay, example 8. It's a circle. So my domain and my range. Remember, the domain is the x value. So what I like to do, especially what I recommend is you're just learning this, I'm just going to trace my pen along the x-axis. What's the lowest x value that I come to when I go to the left? -5. What is the largest x value I hit as I go to the right? 5. And since the graph goes through both of those points, I'm going to put a bracket at both those points to indicate equality. Those points are part of the graph. Now, this is a circle centered right at the origin, so the range is not super interesting. But again, I'm going to trace my pen along the y-axis. What's the lowest y value my pen comes to? Yep, -5. What's the largest y value? Yep, great job. I do the same thing for exercise 9. What's the domain and the range of that problem? All right, so the domain of this, my x values, left and right, and I'm not going to trick you on this. I know you might be like looking at it like, there's decimal? There won't be any decimals on things like this, okay? I'm not into tricks or gimmicks. I just want to see, can you identify? So what do you think is the lowest x value as you go to the left? Yep, -2. What's the largest x value as we go to the right? 6. Yep, I'm going to put brackets around those because the graph goes through both of those. How about the range? What's the lowest y value as I go down here? Yeah, -3. Again, don't question it too much. I make these nice and obvious, hopefully. What's the largest y value? Great. All right, I'm going to work with example 9 with you here. We determined that this parabola was a function. So now what's the domain and what's the range? So I told you this is where those arrows come into effect that I told you about. As I go to the left on the number line, how far left does this parabola go? Yeah, it goes forever to the left. If I had a big enough piece of paper, it would keep going left, 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 left. So you're right. That is -infinity for my lower value. How about to the right? As I go to the right, how far does this parabola go? Again, +infinity. It never stops. Because I have negative infinity and infinity, what do I put at both ends of that? Parentheses. How about the range on this one? How far down does this graph go? -3, so it does have a stopping point. How about up? How far up is this graph going to go? Yeah, it never stops. It's going up really quickly. The -3, I'm going to put a bracket because that is a value it does reach. The infinity, I'm going to put a parenthesis because you never get to infinity. All right, exercise 10, one more. Go ahead and find the domain and the range of that particular parabola, please. All right, so the domain, left and right. How far left will my pen go if I follow this graph? Negative infinity, yes. How far right will my pen go as I follow this graph? 5, yep. And so parenthesis at the negative infinity, bracket at the 5. How about the range? How far down will my pen go as I follow the graph? Yeah, negative infinity. It does it kind of slowly, but that's okay. When you go into infinity, you got all the time you need. Again, remember, this graph hits the edge of the page. There are parentheses implied. Sorry that the graphing software I use doesn't do that. And then how far up is this graph going to go as I follow it with my pen? Infinity. Again, it's doing it slowly, but it's going to get there. There we go. So what I would like you to do is I'd like you to flip the page. There's 2 problems at the top of the page, 2 more graphs. Now, these are graphs that have a start and a stop point. Okay. Again, the start and stop point is intended to be obvious. Okay, so there's no decimals involved, but go ahead and identify each of those as function or not a function, and then what is the domain and the range. And then we'll be approaching the finish line of this section. All right, so let's take a look at these, and then we'll hit the last topic on our agenda here for this section. So example 10, is that a function or not a function? It is a function. My vertical line test, a vertical line will hit that graph at 1 point every time. And then the domain and the range of this graph. So the domain is my left and right. So what's the furthest left this graph goes? -2, yeah, right here. I'm just going to put a little hash mark right there. -2. What's the furthest right this graph goes? 4. Yep, again, I'm going to put a little mark just so that you can see it. And I'm going to put brackets in both those places. How about the range? What's the furthest down my graph is going to go here? Yep, 1 right here. I'll put a little mark right there, 1. What's the furthest up this graph goes? Yep, it peaks up there at 9. And so I'm going to put brackets at both ends of that. Okay, excellent. How about exercise 11? Is this a function or not a function? Okay, it is a function. Yes, indeed. Vertical line will hit the graph at one place or one point every time. And then the domain and the range. Again, I think finding if it's a function or not a function, I think everyone in here, if I gave you a quiz, would be fine. The thing I'm concerned about, the thing I want you to practice, interval notation. We will be using interval notation every day, okay, as we talk about graphs. It's super, super important. That's why I've done so many of these examples. So the domain, how far left does this graph go? Yeah, -3 right there. Great. How far right does this graph go? 2. Great. And then my range, how far down does this go? -2. How far up does it go? 3. Great job. All right, so we've talked about relations being given to us as sets of ordered pairs, and then as tables, then as mappings, then as graphs. The last thing we're just going to do is we're going to talk about function values and being able to find values of different functions. So go down to example 11 right here, finding function values. What we're going to do, let me get mine, is we are going to turn our attention to example 4. We're going to go to the function in example 4, and we're going to find the following values. We're going to find the function value at 3, function value at 7, function value at 11. Now, just before we turn there, you've seen function value I'm anticipating before. Again, it's part of intermediate algebra. The value in the parentheses represents what? The x or the y? Represents the x. Okay, so let's go to example 4, and we are going to look at what's the function value for the x value 3. So here is example 4. It's this set of ordered pairs. Where do you think I'm going to look? What do you think is the function value at 3? Yeah, here is the x value 3. I'm putting a nice green line under it. So what is the corresponding y value? It is 5. Yes, so we come back here to the back page. The function value at 3 is equal to 5. Let's do it again because it's so much fun. The next one's 7. So when I go back to that set of ordered pairs, what is the function value at 7? Yep, everybody tracking with that? Okay. Again, I'm going to put a couple of these on the test. My intent is that that's nice and easy points for you to mop up, but it also is telling me if you understand what the set of ordered pairs, that relation is telling us. Last but not least, turn back to example 4. What's the function value at 11? And when we look at example 4, what do we notice? There's no 11. So here's what I write in that instance, that this is not defined by this function. There's no relationship defined. I do the same thing. The one just to the right, exercise 12 says, go to example 5. I think it's on page, no, I think it's on that front page again. No, it's on page 2. Example 5, it's the first table. Go to example 5 and find the function value at -6 and the function value at 11. All right, so as we flip back and forth, we're finding the function value at -6 and the function value at 11. So looking at my table, what are you going to write down as the function value at -6? Yep, it's this one right here. The y value, the output is 2. And then how about 11? What's the function value at 11? As well, 2. Okay, so when I go back here and I write down my answer, when I input -6, the output is 2. When I input 11, the output is 2. Exercise 13, do the same thing for example 6. That is the first mapping on page 2. So for the first mapping, find the function value of 7 and the function value of -8. All right, when I go to the mapping, I want to know what is the function value at 7 and the function value at -8. So looking at the mapping, what is the output when I look at the x value 7? Okay, it's 5, yes, right here. That's where the arrow leads me. And what's the output when I look at the x value -8? What's not defined? There is no x value -8. No relation is defined. So for exercise 13, this one is 5, and this one is not defined. Excellent work. One more. Go to the graph in example 9. In example 9, find the function value at 6. Okay, look to the x value 6 and determine what the y value is. I'm sorry? All right, well, let's see. Example 9 is right here down at the bottom. It's the parabola. And I asked you what's the function value at the x value 6. So where I'm going to go is I'm going to count over 6 units. 1, 2, 3, 4, 5, 6. To this right here, I'm going to make a dot at that x value. And what is the y value that goes along with that x value of 6? The graph goes through what? -1, yes. Okay, great. There will be a bunch of reading graphs in this class, so that, again, is a very important skill. Okay, we're almost done. One more thing to do, and then we can close up shop on this section. What if my function is given to me as an equation? So this problem in example 12 says my function, the way my x's and y's relate is when I input an x, the y value is going to be defined like this, 5 minus 2 times x. So when I put in 4, here's what I like to do. Okay? This is just my recommendation, just to avoid mistakes, especially sign errors, which are really easy to make, is I would first write down my function like this, 5 minus 2, and then instead of an x, I'm going to put some parentheses. That's where I'm putting my missing value. And in this case, the missing value is 4, so I'll plug in 4. Now it's just arithmetic. What do I do first? Do I do 5 minus 2 first, or I do -2 times 4 first? Yep, multiplication comes first, so that is going to be 5, and then -2 times 4 is -8, and then 5 minus 8 is -3. Please do the same thing for the function value at -5, right below it. That's your example to do right there. All right, so I'm going to do the same thing. My first step is I'm going to rewrite my function as 5 minus 2 times parentheses. And in those parentheses, I'm going to put the value -5. And again, order of operations says I'm going to do the multiplication first. So then that's 5, and -2 times -5 is +10. And 5 plus 10 is 15. One more for you, one more for me. So exercise 15, I've just changed the function a little bit. I've used the letter G to define the function just so that we didn't conflate the two. So this says G of x is going to be 3 times the x value minus 2 times the x value squared. So when I plug in 2, here we go. I've got 3 times my x value. I'm going to put parentheses, minus 2 times my x value, parentheses, squared. Okay, I just like to leave a little blank. I get easily confused. So I'm doing that for me. I recommend it for you. And I'm going to put a 2 into each of those parentheses. What does the order of operations tell me I want to do first on this problem? Exponents. So, I mean, you can do more than one thing, but I'm going to be a legalist here. So I've got 2 times 2 squared. 2 times 2 is 4. I don't square this 2 that's out in front because that is the 2 that was there. Now I'll do that multiplication. 3 times 2 is 6, and then -2 times 4 is -8, and that turns out to be -2. So the input of 2 produces the output of -2. Our last problem for this section, do the same thing with that same function. This time, though, you're plugging in 3. All right, so 3 times the x value minus 2 times the x value squared. 3 times the x value is -3. -2 times -3 squared. Again, I'm going to do my exponents first. So I have 3 times -3 minus 2. -3 squared. What do you get when you square -3? +9. So there's a 9 now right there. I'm going to go ahead and do my multiplication. 3 times -3 is -9. -2 times 9 is -18. And -9 minus 18 is an output of -27. And there we go. That is our function value, and that is the end of section 1.2.